Okay, so thanks everyone for coming. Also, I'd like to thank the local organizers for making this talk possible. And I will talk about discrete Schrodinger operators on Z. So the operators will act on L2 of Z. Can you hear me well? Okay. So, and before talking about quasiperiodic operators, I'd like to say a few things about general Schrodinger operators. So an operator that looks like this. Yeah, I forgot to say that the results I'm going to present are joined with Lynn Gurugia from University of California, Irvine. Yes, so this is discrete Schrodinger operator. We'll assume that V is a bounded real-valued potential. And I'll talk about something that's called ballistic transport or ballistic motion. And to define it, let me introduce the coordinate operator, which is defined like this. So just an operator of multiplication by the index of the component. And in quantum mechanics, it's an operator that measures the position of the particle. And like always in quantum mechanics, you can consider the Schrodinger evolution of the initial state by the Schrodinger equation, or you can look in the Heisenberg representation and measure the position of the particle at moment t. So this is the operator x of t, which is e to the ith, x e to the minus ith. So the operator x of t measures the position of the particle at the time moment t. It's an unbounded operator, but in a few moments I will reduce it to something bounded. Okay, now, what is ballistic motion or ballistic transport? So first, informally. Informally, it means that the particle is moving away from the initial position with linear speed, or speed bounded from below. So the position of the particle is proportional to the time. Okay, I also apologize about my handwriting. I haven't used the blackboard for more than a year. So if you can't read something, please let me know. I'll rewrite it or read it for you. Okay, so informally, ballistic motion means that, for example, x of t psi, let's say the norm, is roughly absolute value of t. So there are several different meanings for the symbol. I'll say a few things in a moment. So yes, and if you take the square of this thing, it's going to be x of t squared psi psi, so it's going to be the second moment of the position operator, then it should grow as t squared. So, but informally, this means that the particle escapes from the origin with a distance proportional to the time.
There is no need to write it.
The second.
The first exponent, exponential ith to the left. No. I mean
the second.
simulation.
Oh, here?
The first, if you
Well, it doesn't matter. There is one exponent to two exponents because it's a unitary operator. Yeah, so so this is one of the equivalent formulations. Well, equivalent modulo explaining what this means. All right, and it is widely believed that ballistic motion should correspond to absolutely continuous spectrum. And there is a general result, which is referred to as Jarneri-Combs last theorem. That if the initial data belongs to the absolutely continuous subspace and the domain of operator x, then this thing grows linearly in time if you take a C0 type average. So basically, it's something like this. 1 over t, integral from 0 to t, norm of x of t psi dt is greater than or equal than c depending on psi absolute value of t. So where psi belongs to the absolutely continuous subspace of H, and let's assume that it's also operator X is well defined, but I'll talk about this in a moment. Okay, so this is basically the only, there are different versions of this result with different moments, also in different dimensions. And yeah?
On the right hand side, you have T capital.
Oh yes, thank you. Thank you very much. Yeah, T capital. And it only happens for sufficiently large T, let's say, depending on psi. So it's the result for large times. And this is, versions of this result is the only thing that I know that hold for general operators. So question is, can we do something better? And let me introduce two definitions, which will probably not really make much sense for now, but it will be clear in a moment. So first, let's say that we have ballistic motion. If this thing grows as the first power of t without the Cesaro average operator. So let's x of t psi. Let's put t capital here. Psi. Okay, so it's a stronger version. Already, there is no general theorem on when this thing holds, but there are some examples. But I'm going to be talking about something even stronger, which is something that I will call strong ballistic transport. Okay, so and this is the following, the answer to the following question. So, okay, so it grows linearly as t. It can't really grow faster than t. So let's say that we divide by t and see what happens. And so let's try to calculate like the limit 1 over t, x of t. Okay, so we will say that the operator h satisfies strong ballistic transport if this family of operators as t goes to infinity converges strongly to some operator which we'll call q. Okay, so and the kernel of q is trivial. Okay, so what does strong convergence here mean? So these operators are unbounded, but I'll make a quick calculation right now, basically to explain what it means. And kernel of q is trivial means that basically any initial data will grow linearly with time. And strong convergence means that after proper rescaling, the wave packet takes a very particular shape. So basically it takes the shape described by the operator q.
The strong ballistic transport. You have to apply x of t to psi, or there is no psi.
Well, this is operators now.
Okay.
So it must be true applied to any psi in the domain of x.
That is why strong.
Yeah, but I will remove this condition in a moment. So I'll write a different definition, which is essentially equivalent. Okay, so basically it tells you that if you consider the large time asymptotics of the operator x of t, then you can calculate the first order term in time. Okay, so let me talk a little bit about strong convergence and also do something that will make us forget about domains of definition. So let's consider x of t minus x of 0. And you can write this as the integral of derivative. Okay, so and then if you calculate this derivative using the expression for x, what happens? If we differentiate this with respect to t or this with respect to t, we get IH on the left or right hand side, so in that we get the commutator between x and h, right? So it's integral from 0 to t. Use the ITH. Okay, so IH. maybe I got the sign wrong, but it should be something like this. And then if we commute x and h, okay, let's call this operator A. And the nice thing about this operator A is that first it's bounded, and second, it actually, the potential completely disappears. So A psi n equals something like I psi n plus 1 minus I psi n minus 1. So it's like the Laplacian operator, but with I and minus. Okay, so and then what happens if we divide by t? If we divide by t, we get 1 over tx of t, which is what we want. 1 over tx of 0, which just disappears, as long as psi is in the domain of x. So, and then it makes sense just to, instead of using x of t, just use this difference. So to say that the particle gets away not from the origin, but from the initial position. And then it becomes something you can write down in terms of bounded operator. So from now on, we'll just use this definition, which is equivalent for all practical purposes. Okay, so in other words, we are looking for something like this. 1 over t integral 0 to t e to the ith a e to the minus ith dt converges strongly to the operator q. So this is the equivalent definition of strong ballistic transport. And
The question is, what is Q, right?
well, the question is it true for some reasonable classes of operators? I mean, from now on, it's completely unclear, like whether it's even possible, right? So the operator must be really nice. And if yes,
But
what's the
Q is
operator?
unknown also.
Q is also unknown, yes. So the second question, if it's true, can we calculate Q? And can we prove that kernel of Q is non-zero? Okay, so yeah, okay, some names also. So the operator A is sometimes called the current operator. And Q is called asymptotic velocity. So like the speed of the particle at infinity. Okay, as I said, well, obviously, this result, if the kernel of Q is non-zero, implies that result, ballistic motion. And even for that result, there are no general results. So there are some concrete classes. For here, there are also concrete classes. So the first class of operators for which this became known is periodic operators. So the first, this idea with convergent operator Q was found by Ash and Knauf. I forgot the year, but the paper is called Motion in Periodic Potentials. So this was for Schrodinger operators in the continuum. So in that case, A becomes a gradient operator. And later it was discussed for the discrete case by Domanic, Lupich, and Yeltsin. And also later, Jake Philman so by approximation, he derived a result for limit periodic operators from the result from periodic operators. Okay, so the motivation here, I guess it was just because it looks very nice, right? So we can calculate the complete first term of asymptotics of some observable infinity. Here, they actually had a very concrete application. So it was used to estimate from below Lieb-Robinson bound on Lieb-Robinson velocity in some xy spin chains, which is an integrable model, so which reduces to some Schrodinger operators. And for the reduction procedure is non-local, so they need very strong transport properties for the Schrodinger operator to make conclusions about an integrable model. But that was just, we'll only talk about Schrodinger operators in this talk. I'm just saying that it was motivated by some integrable models in many-body physics. Okay, so, and the question I'm going to talk about is the next natural class of operators with absolutely continuous spectrum, well, for me at least, which is quasiperiodic operators. So let me talk about quasiperiodic operators. Maybe I'll use a new piece of board. Well, okay, so I guess you can say that next natural class of operators of the AC spectrum is something like perturbations of the Laplacian with compact support, but this result is actually, in some sense, stable under small perturbations in which scattering theory works, in some sense. So I want some class which is not a perturbation of another class. Quasiperiodic operators. So let me talk a little bit about them. Suppose you have a function on the torus, V, C omega. For now, it's going to be an analytic function, d-dimensional torus, real valid. And C omega means real analytic, yes. Okay, so and then consider a Schrodinger operator of the following form. Okay, so let's also h of x psi n discrete Laplacian plus some small parameter epsilon v of. Okay, so let me first write it and then explain. X plus n alpha psi n. Okay, so here x is some point in the torus. And d, so in the quasi-periodic language, this operator is called a multi-frequency quasi-periodic operator with d frequencies. Well, assuming that alpha is a vector with rational independent components. So x is some point in the torus, n is integer, so an alpha is a vector. And okay, alpha, I guess, the frequency, let's say it can be from RD or from the torus, it doesn't really matter. Okay, so, and alpha must be a vector with rational independent components. So 1, alpha d, independent over Q. Over Q or over Z, it doesn't matter. So otherwise, I mean, for example, if they're all, yeah. So they have to be independent over Q for the operator to be quasi-periodic. And we will consider the regime of small epsilon. Yes, so if the epsilon is small, roughly, you can say that the operator should behave like the Laplacian. But of course, it's not a compactly supported perturbation, something like this. So rigorous results are obtained by different methods, including KM theory. So what I want to say is that to make this V a legitimate small perturbation of the Laplacian, you also need to introduce some conditions on alpha to solve problems of small denominators. Anyway, so the regime I'm going to be talking about is where alpha is a Diophantine number. So let me define what Diophantine number is. So alpha, yeah? Alpha dc, d-dimensional of, let's say, c tau, if distance n dot alpha z, frequency minus tau for n from zd minus the origin. So in other words, alpha is not very close to the rationals. Okay, and so some results about quasi-periodic operators, it summarizes many papers, but roughly is epsilon, if alpha is Diophantine, epsilon is small, the spectrum of such operators will be absolutely continuous. So, oh yeah, also tau always will be greater than d plus 1. And in fact, for simplicity, let's just fix some tau, that's some tau greater than d plus 1, for example, I don't know, 10d, because the larger tau, the weaker the condition is. And if we fix any tau, then, and take the unit over all c, then it's going to be a full measure set. So the remainder correction will be of 0 measures. So epsilon less than, yeah. And the regime of absolutely continuous spectrum for d greater than 1, we have absolutely continuous spectrum for epsilon less than epsilon 0 of the potential and difference in constant. And for d equals 1, it can be shown that it has absolutely continuous spectrum for epsilon that is independent on the difference in constant, dependent only on potential. So in both cases, the constant also depends on tau, but we just fix tau. The reason I emphasize on these things is because in this result, it's possible to find epsilon that would serve at the same, that would make it possible at the same time for a full measure set of frequencies. Here, the set of frequencies, you always have to remove some small measure subset. Okay, so and then this was the next natural class of operators with AC spectrum, and there were some results about ballistic motion stroke ballistic transfer. So 2016, Zhao proved ballistic motion in this regime, which is called also perturbative regime. So it didn't cover this case. And also, there was my paper. So it was possible to prove strong ballistic transport, but it was strong ballistic transport in expectation. So what's the result? So let me say it more precisely. As I said, it's natural sometimes to consider the family of this operators as a family in X, and also sometimes to take a direct integral. So if you take a direct integral of this family, it becomes a much better operator. So so consider integral H. Well, let me just say the result. So 1 over t integral 0 to t integral e to the ith of x a minus ith of x dx dt converges direct integral q of x dx. Strongly. Okay, strongly, but in the direct integral space. So roughly, it's a result of convergence in expectation, if this x is considered as a random variable. Okay, so the advantage of this thing, well, this thing was, I mean, this, in a way, this is a stronger result because it tells you the convergence at every single x, but it only gives you ballistic motion. This result gives you the convergence, strong convergence to q of x. I'll also tell you what q of x is. But it only happens in expectation. Another advantage of this result is that you can also cover this regime. So, yes, so this result can cover only perturbative regime, and this result can cover non-perturbative regime. Okay, so, and what is q of x? So q of x actually has an explicit formula, more or less. Let me introduce the integrate density of states of a quasiperiodic operator. So it's the following object. N of e equals integral over td. Can you hear me? Or? Okay. So integrate density of states is basically the expectation of the spectral measure applied to the zero basis vector. So let's take spectral projection h. Okay, let's write it like this: minus infinity e. So this is the indicator function applied to h of x Now this is the spectral projection, and apply it to the basis vector of the origin. So let's assume that the measure on the torus is normalized to 1. So this is called the integrated density of states. So it's a distribution function of the density of states measure, and density of states measure is the average of spectral measures. There are several other definitions. You can use box counting of box eigenvalues. But this is the most simple one. And then you can calculate this function. Let's call g of e to be 1 over of pi times 1 over n prime of e. Okay, so n is the non-decreasing function, so derivative makes sense, but derivative can sometimes be 0, right? So 1 over this function is not defined on the whole real line. But n prime of e is non-zero almost everywhere on the spectrum of h. So you can still calculate g of h of x. This is going to be q of x. Well, so if you actually compare it with the result for periodic operators, you could have guessed this formula. But so there are several different technical things which come to this calculation. I don't think I will be able to mention them. Yeah. So basically, there were two results. There was a result which gives you the true ballistic motion without any average and expectation, but it's only a lower bound. And there was a result that gives you like explicit calculation, but can only be done in expectation. And so one of them was covered, answered some questions, this other question, also answered other questions, sorry. Yes, and the motivation for the continuation was that basically, is there any way to improve this result so that we can recover this result? So in other words, is it possible to remove this direct integral here and get a result almost everywhere or everywhere? And the main result, okay, so the main theorem is that in these regimes, so there is epsilon 0 like this, then it's possible. That is possible. So we actually get this result for every x. This is the main theorem. I don't know how to write it, just so let's call this regime the AC regime. Although I'm cheating a little bit. So AC regime says that there exists epsilon depending on these two things, that the spectrum will be AC, and we will need something else. So if I have time, I'll tell about that something else, which also happens for epsilon less than epsilon 0 dependent on VC, but it might be different epsilon 0. So for sufficiently small epsilon, we have both AC and another thing, which is the assumption of our theorem. So that's the result, but I just want to make the minimal understandable statement of the main results for now. So I can give more details if I have time. So we can remove well, and also let me also give some remark that in this regime, it almost becomes if and only if results. So the assumption that we need, which is basically full measure reducibility, actually appears for Defontaine alpha, it appears at the same time as AC spectrum. So that additional condition that I didn't mention implies AC spectrum. In general, it's stronger, but in the dimension 1 and Defontaine setting, they're actually almost equivalent. Modulo something else, which I will maybe mention later. So this is the result. Now let me tell you several ideas of the proof, unless you have some maybe general questions. Yeah?
Trying to make sense. Under certain assumption, this assumption can be removed.
Oh, sorry, this is just a typo. I'm sorry, I was thinking about one thing and wrote the other thing. So you can remove the direct integrals. You can get convergence actually for all x
And
to
start is
the
second
operator defined by
condition,
this formula.
right? Start is for the second condition.
For both. So we can do both
Right.
this regime and so for
Is this or
yeah,
this?
for d greater than 1 we can do this. For d equals 1 we can do better. We can do this. So but the main result is the conditional result. It's basically derivation of this convergence from something that happens in these regimes. Okay, so basically it tells you that in many cases the spectrum of quasiperiodic AC spectrum of quasiperiodic operators is very nice. That if you take initial data, take large time asymptotics, it actually has well-defined asymptotic velocity. So the particle travels on infinity. You can kind of describe how it travels on infinity. I don't know if this has any physical importance, but I think that's interesting. And this velocity is actually explicit. Okay, some discussion about the proof. Okay, so we're calculating this limit. Let's talk about it in abstract setting first. A e to the minus ITH. And let's do something which seems very unnatural. So we want this limit to calculate this limit in the regime of AC spectrum, but for the sake of the argument, let's assume that H actually has point spectrum. Suppose that H has a basis of eigenfunctions. And let's try to calculate this limit. So what do we get? Let's just calculate it. Okay, so what I'm going to calculate is the weak limit, but you can check that in this case the strong limit will exist. It will be the same. Let's calculate. Let's call this operator A of t. So again, this is a little bit abuse of notation because this is not the Heisenberg evolution of A. It's this operator, but definition is written. Let's calculate A of t. Ck, Cl in the product. Right, so what's going to happen? If we act by this on psi k, this ITH will going to give you e to the minus ITEK, right? And this e ITH we can move on psi l and again calculate it. So in the end we get integral of 1 over t integral e to the IT EK, yeah, maybe with a minus dt, a psi k, psi l. Okay, yes, so I was scared for a second because I thought it's going to be two pluses, but yes, so we get 1 minus when we move this to the right, and then we get 1 minus when we move this exponent back to the left. So this is correct. And then this integral can be calculated. Oh yeah, let's make another assumption. Let's also assume that the spectrum is simple. So then it's very easy to calculate this. If k equals L, then it's just going to be 1. If k is not equal to L, then you get something like sine of t over t, and it's going to go to 0. And you can check that the convergence is actually going to be strong. So then, for this operator, the analog of operator Q would be just the diagonal part of the operator A in the eigenbasis of the operator H. So this is the answer. Well, I have to use this angle and brackets, I guess. Okay, so basically, this AIT has an operator theoretical meaning because it's an operator that kind of removes everything from A except the diagonal. But the catch is that it's in the regime of point spectrum. We want in the regime of AC spectrum. And I don't know any analog of this result for the AC spectrum. But let's go back to our cases. And let's start from the periodic case, actually. And I can now tell you the proof of the periodic case basically in one line. So periodic case. So you have a periodic Schrodinger operator, it admits Floquet expansion. Right? And then if you want to calculate this limit, just apply it to the Floquet expansion and then make the same procedure at each Floquet fiber. So for some k, you might not have simple spectrum, but for almost all k, you will. And if it's not a simple spectrum, then anyway, you'll get something like the projection on the eigenspace here. So it's not really even giving you trouble. So basically, in the periodic case, the results by Esch, Knauf, Domanic, Lukic, Jessen, all based on this observation, that in the each Floquet fiber, we basically remove the off-diagonal entries. And then the calculation will involve something with the band functions, which can be interpreted like this. Okay, now, what to do with quasiperiodic operators? What to do with quasiperiodic operators and why direct integrals simplify the life very, very much. So we can use something that's called Aubry duality. If instead of individual operator we consider the direct integral, h of x is a quasiperiodic operator that I defined before, which I already erased. But this is an abstract result for all quasiperiodic operators, so there is no de Fontaine or anything. So it's just algebraic relation. So this direct integral is unitarily equivalent to another direct integral. So integral, let's call it h tilde of theta d theta. And h tilde of theta will also be a quasiperiodic operator of a more general form. So first, theta will be a one-dimensional parameter. And then the formula, okay, so h tilde of theta, the parameter will be one-dimensional instead of multidimensional, but the operator itself will act on a lattice. So h tilde of theta, I will act on L2 of ZD. Okay, sorry, I'm gonna move this to the top. I'm switching it too much. And it will look like this. So h tilde psi m equals. Okay, so it will have kinetic energy part and potential part, and basically the role of potential and the Laplacian will switch. The kinetic energy part will be convolution with the Fourier transform of the original potential. So epsilon v hat convolution psi m. And the second part will be m dot alpha. This is an inner product plus theta psi m. Okay, so and how does this unitary equivalence look? So how to get this operator from the original operator? So basically what you need to do is you need to consider the space in which this operator acts as functions of two variables, one continuous variable and one discrete variable, and just do Fourier transform in both variables. Then they're going to switch their roles. And also you need to move the quasiperiodic part from one variable to another. So informally, you can write this transformation like this. Psi, originally we had psi of xn. It will be mapped into, so it's a little bit abuse of notation, but I think it's easier to understand it like this. Psi tilde, I'll explain what psi tilde is. M theta plus m alpha. Tilde means that we did Fourier transform in both variables. And once we do the Fourier transform, you're going to get a function of the variable m, which is dual to x. So x is from td, z, zd, t. So we get psi tilde of m and theta. And then you have to replace theta by theta plus m alpha, so that the quasiperiodic part, otherwise quasiperiodic dependence would be here. Okay, so and then morally, what do the operators look like? So they have small kinetic energy and fixed potential. And you can prove that in the regime that we are talking about, these operators will have point spectrum. Well, roughly because this part dominates, and we still have difference in properties, but you can also prove it directly from the assumption that I didn't mention about the C spectrum. So anyway, so in the regimes we consider, these operators will have point spectrum. And now we can apply the same procedure. So point spectrum, for almost every theta, also simple spectrum. And then you can do the operation I described here in each fiber and get convergence. Okay, so this is what we get on the level of integrals. So this is how you prove the 2016 result. So now, the main idea behind the improvement is that it's the following question. Okay, so to remove the dependence, to improve the convergence, basically you want to study the operators finite T and look at their behavior in X. If you have some kind of uniformness in X, then you can improve convergence from L2 to, for example, L infinity or even C. And how do you do this? Well, and the observation is the following, that the regularity properties of the operator H in the variable X are roughly, okay, so let me be more precise. You want something like L infinity in the variable X. Originally you have L2 in X and L2 in the integer variable. So you have L2 in both variables. Now you want to improve one of them to L infinity. So to do it, you want to improve the dual variable to L1. So L2, originally we have L2 of TD, L2 of Z. Duality maps like this, L2 CD, L2, well, okay, so not it's cross, sorry. L2 ZD cross T. Okay, so we want to improve L2 in this coordinate to L1. To L infinity, which means roughly that we want to improve this ZD to L1, right? So and this ZD corresponds to the behavior of the eigenfunction of this operator on infinity, and the eigenfunctions are localized. So they decay, well, in this regime they decay exponentially, but the decay is not uniform in theta. So we need something that you can, that's either uniform in theta or at least survives some integration in theta. And one possibility to do it is to consider a dynamical localization. So let me give a simplest example. In expectation, so it's a result which can be formulated like this. So let's say we consider e to the I t h tilde of theta applied to ek L. So basically we're looking at the exponent of the Schrodinger evolution of the operator H and look at its matrix elements. So we want them to decay exponentially in expectation. C1, C2, K minus L. Okay, so and this is the simplest example of sufficient condition that we get. So basically, in addition to purely point spectrum here, we want to have some control on decay of the eigenfunction, which is not possible uniformly. but possible in expectation and theta. And once you have a result like this, you can improve this thing from L2 to L1, and after several pages of calculations, you can show that you can do convergence. You can remove the direct integral. Okay, so this is the main idea, and this is the simplest example of the technique that we have. So there are some other cases that we can cover, but that probably would be too much detail. So how much time do I have?
2 minutes.
2 minutes. Okay, so let me tell you something interesting that came up. No, I mean I had just one last thing to mention, which I think is just interesting. So basically, when we were writing the proof, we were calculating. We were trying to. Okay, so if you have this, you can immediately say that we have convergence in L infinity in the measure critical sense, but in the end, you get convergence for almost all x and not all. And because the direct integral doesn't really capture zero measure sets. So how to go from almost all to all? So basically, we compare two things. We compare the expression at finite time with its limit. So in which, if we have some uniformness, we know that the expression in finite time is uniformly continuous in x. And now if we knew that q of x is continuous in x in a strong topology, we would be done. And that looks like a very simple question. Suppose you have a family of operators with, let's say, AC spectrum, very continuous in x, so it's actually an analytic parameter in the matrix elements. So definitely it's strongly continuous. And you have some measurable function. So is it true? And well, it seems very true. In fact, if you do it, for example, for indicator function of the interval, it's going to be true. Finite linear combination is also going to be true. And then you want to say, okay, let's do arbitrary measurable function by approximation. And in general, you can't really do this. You can do it only for Jordan measurable functions. And we need to do it for this function g, about which we don't know much. So this is one of the places where that another assumption was used. So actually, we need some additional data about the dependence of spectral measure of h in the variable x to make it possible. So and that dependence is through something that's called reducibility of Schrodinger co-cycles. So yeah, I don't have time to go into details, but it was something that was interesting, that you cannot prove it directly.